So basically today I will only speak of experimental results that we have done with Tristan Gillet in Belgium, in Liège. So basically the question we had, So the question we had is about the interference in the walking droplet experiment. So we know that at the long time scale, it's well accepted that there are indeed interferences, and it has been shown like more than like almost 10 years ago by Dan Harris in the group of John. But at the fast time, let's say at the middle time scale, which I call dynamical, we are not sure. There is no definite proof that these interferences occurs. So, for instance, I just showed the data from Pucci and all, where the droplet definitely sees the second slits in the double slit experiment, but we cannot tell if there are interferences or not. And the experimental difficulties lies on the fact that capillary waves in the walking droplet experiment are damped by viscous damping, but also because we don't really know very well the interaction of the capillary wave with the submerged boundaries. We don't know how they are reflected and damped. So our motivation is, can we get rid of let's say submerged boundaries to show dynamical interferences? And there is an experiment in quantum mechanics that would make it. This is the Umandal Experiment, when two quantum particles are sent onto a beam splitter, and if they are fermions, they just behave trying to avoid themselves. So they are always on different sides of the beam splitter. And in the case of bosons, this is contrary, and both particles go together. So to make this experiment where there are interferences, we need a beam splitter that doesn't exist in the walking droplet experiment. So my talk will be about the design of a beam splitter for walking droplets. And so at the beginning of our thought with Tristan, we had two options. And I will basically speak of the first one and refer to the paper we wrote with Tristan, Peter Schlegek, and John Bush about the tunneling, which is simply a submerged barrier on which you send a particle, and the particle may cross or not. So you can divide a beam like that. The second option is the standing wave, and we'll see how we can divide a beam of particle with a standing wave. First, the experimental setup. It's as usual. There is a shaker on top of which there is a bath with textured background. And the peculiarity of this setup is that there is a groove inside where the Faraday threshold may be crossed, and the rest of the bath is at a limited depth where the Faraday threshold is not crossed. So I remember that John spoke about crossing the Faraday threshold as a Loch Ness monster, but now we are trying to control that. So our experiment is protected from air currents with the lead, and this is the cross section of the experiment with the groove here. And so where there is at the groove position, there is a large depth, and everywhere else there is a small depth and a smaller depth on the sides to avoid radiation of capillary waves from the sides. And the droplet is then just looping around this this path, and it's deviated either on the right or on the left. And at the same time, so we measure the capillary waves within the Faraday wave within the groove with a synthetic shearing technique. And the peculiarity of this setup is that the feedback loop is not done onto the acceleration of the shaker, but on the wave 8 of the Faraday wave in the groove. So here is what we can observe. So here is the Faraday waves, the standing Faraday waves, and we send here a droplet. The droplet interacts with the wave, and it's deviated, so either on the right on this example, then it loops around, and it sends toward the same wave, and it's deviated on the right, on the left, sorry. And this can be done several times, and so we did almost 2,000 launches like that, and we recorded the velocity of the droplet, the height of the Faraday wave, the impact parameter, and the velocity of the droplets. Okay. So the most important parameter is the impact parameter. It's the distance between the maximum of the standing Faraday wave and the position of the particle far away from the groove. So it's here. This position is delta x, and then we divide this position by the Faraday wave length, lambda f, and this gives the impact parameter, which we modulate by a factor pi when the droplet is either flying, like here, or impacting, like here. So that's the impact parameter. And now it are the results. So these are the trajectories observed. Each point corresponds to a droplet impact. And the gray area here corresponds to the groove where is the standing Faraday wave. What we observe is that the droplets are deviated far away from the groove. It's because the groove radiates some waves. So the droplet is sent on the left and it's deviated instead on the right, and it's deviated on the left. And so basically what it does is like it chooses one of the three valleys that you can see here, so the red, the green one, and the blue one. And after it has chosen the valley, it's again deviated by the waves. Okay, so our boom splitter are some defects. Basically, they are more particle deviated on the right than on the left. Right now, I don't know very well why it has this behavior. And there is also another representation of the third, so the third valley in the data. So here is the phase space where we represent here impact parameter phi, and here the wave amplitude. And on the left, here is color coded the diffraction angle. So when it's coded blue, it's deviated on the right, and when it's coded red, it's deviated on the left. And what you can tell from this image is that there are few parts where in every part of this phase space, you can have blue or red dots. here corresponds to the chosen valley in 3 colors. So blue, it's valley 1 on the bottom, green, it's in the middle, and red on top. And as you can see, like there are spots where there are only blue points, only green points, or only red points. There are also some parts of the phase space where it's mixed. So basically what it tells is that it's deterministic in the choice of the valley, but then it's chaotic for the choice of the diffraction angle. Here is the probability graph that we obtain for the diffraction angle. As I told you, there is some more particle diffracted on the left than on the right. But anyway, what we see is that there are basically 3 peaks, and that the peaks are centered about minus 30 degrees, minus and plus 30 degrees, and at 0 degree. So this is a different diffraction compared to the one observed for the 2 slits experiments, where the maximum angles reach 60 degrees. So finally, my data set allowed me to test the dependence of the diffraction angle with the wave height. And here is plotted data points taken for the same particle, the same droplet, but with so the same impact parameter, but with different wave heights. And as you can see, the diffraction angle goes from blue to red, meaning that just changing the wave amplitude changes the direction of the diffraction. And here are the trajectories. So basically, they all start at the same point. Then they are grouped within the valley, and then after the valley, they are diffracted in every direction. Okay, so I don't know if I have much time. I've been quite quick. So maybe John. So the rest of the talk is about the tunneling experiment with walkers, and it's quite long. So I may prefer to stop there if it's okay for you.
Yeah, we can certainly take another 10 minutes. Maybe just do a quick overview. Or...
Okay, let's go for a quick overview for tunneling walkers. So this is a work I've done with Tristan Gillet and Peter Schlegek from Liège University and John Bush from MIT. So basically, we reproduced the tunneling experiment made by Antonin Eddy and Yves Couder, where a walking droplet is sent toward the submerged boundary. So basically, there is less oil onto the boundary, and it acts as a repulsive potential. So here is the results of Antonin Eddy with a transition between no transmission to full transmission above the barrier of 4 millimeters per second. And we wondered why this classical tunneling could be unpredictable. So we reproduced the same experiment, but now we tried to kill the variability that exists in the walking droplet experiment. And the first step was to use only one droplet. So this is our setup, and basically the droplet is just looping around the setup, so crossing or not. So if it's crossing, it just goes there, and then it's sent again, and so on. So it basically allows to send the same droplets multiple times on the barrier. So here is what we can observe. So sometimes the droplet is reflected, and sometimes the same droplets, the very same droplets is transmitted. So we fix the same memory, we fix everything the same, but sometimes it gets transmitted, sometimes it does not. So the first thing I did, it's varying the driving acceleration. So it's the same droplet, but with varying the driving acceleration, we change a little bit the memory, and we get different velocities. And we observe here the same as Antonoidy, with no transmission when the velocity is lower than 11.8 millimeters per second, to 100% of transmission when the velocity is larger than 12.2. But in our setup, the transition width is only 0.4 millimeters per second, which is 10 times smaller than Antonoidy's observation. So this is due to the control on air currents and reproducible incident angles. So yeah, so that's so basically we have a deviation in incident angle of 0.1 degree, and we had free walking velocity that does not depend onto the room temperature, which was controlled, but which were there were some variations. So it's so the transmission, as you can see here, there are red and so red correspond to transmitted and black correspond to reflected, and it does not depend neither on the incident angle nor on the walking velocity nor on the room temperature. So it's definitely not a classical point mechanic result. So to understand why tunneling should be unpredictable for walking droplet, we decided to zoom at the fast time scale with a high-speed camera. So in space, the intercept distance is 300 microns, and in time, the bouncing frequency is 80 hertz. So here are the launches. So we had 49 superimposed trajectories. So it's always the same trajectory, which is sent onto the barrier. And the data points are just mixed up far from the barrier. So it's the green inset here. And when they arrive onto the barrier, the points just unmix. So the black trajectory corresponding to reflected trajectories just gathers and separates from the red ones. So we tried to understand if we were able to predict the reflection of particle far from the barrier just by looking at the impact position. And so it's what we did, and we tried to compare statistically two adjunct bins. And what we show is that basically we cannot predict just based on the position of the particle if the particle will cross or not the barrier. So we just refined our analysis by trying to understand the phase space. So to do it, we plot the data points as the distance to the barrier and the velocity of the walker. And here what we see is that far from the barrier, there are fluctuations of the velocity of the particle depending on the position. And second, we see that we can predict quite far away that black dots and red dots separate. So it separates a bit before the barrier when we consider distance and velocity as the reference phase space. So we created a mixed indicator And we were able to define a Demix distance, a distance at which we can tell that the particle will cross or not the barrier depending on the knowledge on both the velocity of the particle and its position. And here it's clearly at the foot of the barrier. So the barrier was 2 millimeters wide. So here it's the half the barrier. So it's a bit before the barrier. And so this point, this Demix distance, this point corresponds to some phase variation of the bouncing dynamics. So we expect that these are the main phenomenon is that there is perturbation of the bouncing dynamics due to the submerged barrier, and that's what creates chaos. And that's something we showed in a previous publication. Then we tried to compare to what can be said with quantum mechanics. So as you know, in the orthodox view of quantum mechanics, you cannot define a trajectory. So to do it, we just tried to repeat measurements. So we measured the position of the particle and its velocity. So we project the wave function randomly onto the projector and so on. So we can define, so we measure the position and the velocity of the quantum particle at different time intervals, and we can define then the trajectory of the quantum particle. So here it's kind of things that we can obtain. So I will just explain exactly what is the repeated measurement formalism. So basically, we have an initial state. So we prepare the particle with a special wave function. So basically, we say that all the particles are corresponds to the wave function of a projector, which is centered on a spatial location and a spatial velocity. So here N stands for the location and L for the velocity or the momentum. So the considered basis is all complete. That means that the particle cannot be missed, and the projector basis is also orthonormal, meaning that we cannot count twice the particle. So here is the expression of the projector, but we won't pay much attention to it right now. So basically, a projector describes a part of the phase space that is here, and it corresponds to a given space location and a given momentum. So what we do is just we start with the particle in this box, the blue box here, and then we propagate for some time this particle or this wave according to the Schrödinger wave function. So we have the wave function psi, which evolves in time and space. And after some time, we just measure this wave function by computing the probability that the particle is on a different box in the phase space. So this probability is P and L, and P and L is simply the square of the projection of the wave function psi on the projector key. And then we randomly choose according to the probability distribution the new box where is the particle, and this is similar to the process of collapse, wave function collapse on in quantum mechanics. And then we have a new wave function which is in the another box, and then we propagate it again and measure it again and so on. And we call this process repeated measurement formalism. So we are now able to compute the trajectory of a quantum particle, and then we can also compute a mixed parameter for the quantum particle, similarly to what we have done for working droplets. And what we see here. So sorry, I'm trying to go quick enough. And what we saw here is that for the quantum particle trajectories, we cannot tell if the particle will cross or not until we arrive at the foot of the barrier. Similarly to what we have for the working droplet experiment. And this the demix distance scales with the barrier width for quantum particles. So yeah, so what's the difference between worker tunneling and quantum tunneling? First is the behavior. In quantum, it's a probabilistic behavior, whereas for workers it's deterministic, but sometimes chaotic. So the non-locality for quantum particle, it is complete. It's completely non-local. Whereas for worker, it's partially non-local, meaning that there is some extent to the waves around the worker. Both are unpredictable, meaning that if you know and you can measure the position and velocity of the particle, you are not sure that you can tell if the particle will cross or not the barrier. And the source of unpredictability for quantum particles is the wave function, whereas for workers, we expect that it is the vertical dynamics. And the collapse of the unpredictability is made by measurements for quantum particle, whereas it occurs during the evolution of the system for workers. Okay, so I thank you for your attention, and I will be pleased to answer your question. Thank you.